I'll wait for 2-3 minutes more. Okay, so I don't think anyone will join, or they can join us in midway. So, first of all, I welcome you all to the second session of this tutorial, which is on transmission line and electromagnetic waves. So, what we will do, as I promised you, so first, this is just a brief outline of what you have learned in week 1, week 2, week 3. So week 1, week 2 was about transmission line theory, flexion coefficient, bounce diagram, and mostly in the week 3 you studied about the transmission line which have losses. Okay, and third week assignment is on that only. So what I will do now, first, we will do some maybe two problems from the assignment 2, which are based on this bounce diagram and some reflection coefficient. So I thought like these two problems can be little different. So I thought to discuss them, and then what we will do 2-3 questions, which will be based on the week 3, and then we will conclude. So here, first, we will start with some of the two problems from the week 2 assignment. So what I want, like I will put up the question, and then either one of you or anyone want can answer. And if someone has difficulty in that, then we will try to go through the solution. Or if it is clear to the everyone, then we will skip that. Okay, so yes, we will start with the two problems from the assignment number 2. So here is the first problem. So it was the question 1 of the assignment 2, where an impulse which is given by the equation vzt is equal to some function of t and z, and it's traveling on a 10-meter long transmission line where t is in seconds and z is in meter. So there were three parts of the problem. So one is the what is the speed of the wave. Second is the can you tell in which direction the wave is moving? Either it's a standing wave, or it's moving in positive direction, or in negative direction, or none of these. And then it was asked to calculate the transit time. So I think everyone is able to solve this problem. So what we will do, we will just go through the solution of this. So as you know, the expression of voltage on transmission line is already given, and we already know, like, just let me get the laser pointer. So we know that VZT is some function of T and Z, and length of transmission line is 10 meter, right? So, and we learn in our lectures that voltage as a function of Z and T it can be written as f of omega t minus beta z, right, where omega is the angular frequency and beta is the phase constant. So now if you compare this with the given expression, right, so you can see it's some function, here is some function delta and here is some function f. So you, if you compare omega t minus beta z with this expression, you can clearly see that omega is given by 10 power 7 radian per second, okay, and also beta can be written as 5 radian per meter, like that is the unit of beta. Now you know, like if you have both omega and beta, you can easily calculate the wave speed. So wave speed is given by omega by beta, right? So omega is 10 power 7 and beta is 5. So the speed you get on of the signal on this transmission line is 2 into 10 power 6 meter per second. So this was the answer of this first part. So the wave speed of the wave is 2 into 10 power 6 meter per second. Now the second part is what is the direction of this wave. So as you can clearly see, right, so this function, whenever you have something like omega t minus beta z, that means it is moving in the positive z direction. If it is was like omega t plus beta z, then you can say it's moving in the negative direction, or it can be a sum, maybe plus and minus, then it can be a standing wave. So in this problem it's given omega t minus beta z, right? So omega t minus beta z means wave is propagating in the positive z direction. So the answer of this problem is second, option B, which is again a traveling in positive z direction. And the third is very easy, where you were asked to find the transit time. So transit time is nothing, like you know the speed of the wave, you know the length of the transmission line. So from there you can easily calculate. So transit time is given by distance upon signal speed, right? So distance is given by 10 meter and speed of the signal is 2 into 10 power 6 meter per second. So the transit time will be 5 microsecond. Okay, so this was the first problem of this assignment number 2, and I hope it was really easy. Now I will come to the little different problem, which was the fourth problem in assignment. So basically here I am discussing mostly all of assignment number 2, because I feel that is if anyone has problem, then we can solve it straight away. Okay, so this was the second problem. So here it was based on the uh, bounce diagram, right? And such type of problem we already solved in tutorial number 1, right, where I showed you how to draw the bounce diagram, or how to calculate the voltage as some specific distance on the transmission line, or how, what will be the current, or what is the plot of voltage with respect to time at any particular z, right? So such type of problem we already solved, and it was the same problem which is given in the assignment mostly, so it needs basically the same concept. Okay, so here this problem is like you have some circuit which is connected by the battery, which has some voltage V naught, and it has some internal resistance RS, right? And then it is connected to the transmission line, which has characteristic impedance of 100 ohm, and it has some transit time, right? And also it is terminated by some load resistance, which is given by RL. Now in this problem it was given, two things were given, right? So you are given the voltage at z is equal to 0 with respect to time. So basically you know what is the voltage here with respect to time, with respect to different transit time. Similarly, you know what will be the voltage as z is equal to L, right? So here is the plot of that. So voltage at z is equal to L is given by this plot. So if you have this much information, now you need to solve these 7 part of this question. So is anyone here which has who has solved this problem, uh, or they were not able to, like if anyone can respond, like then we can solve this together actually. Anyone who has solved this problem, or who can tell the answers of the different parts, because it's from the same assignment problem only. No one?
I guess sir, I solved it
Huh?
actually.
uh, I am not able to hear you. Hello? Hello, can you speak up again? Hello. Mm, so what we can do, we can go parts by parts in this. So what you can do, you can tell me the answers, whatever you have find, and then we can see whether it's correct or not by going through the solution one by one. Because yeah, we will learn many things from this problem. So I thought to cover it.
Hello.
So can you tell me the answer of like first part or second part?
Acha.
Uh, like this is the fourth.
The first
What is the load impedance? What is the source impedance? What is the value of V naught? Like that.
actually load impedance ZL.
So what is the value of that? Like you have calculated it, right? In the assignment.
Hello.
Yes, I am listening. Hello. Hello. Your voice is breaking. Maybe what I will do, I will go through the solutions and then you can stop me in between if you have any doubts, right? So, first of all,
Yes, sir. So ZL.
yeah. So, what is the value of ZL
So
and yeah,
RL 60
okay, that's
ohm.
correct. 60 ohm. And what is source impedance?
So Z
This is correct. RL is 60 ohm. What is the source impedance? Like, what is the internal resistance of the battery here? The value of RS.
RS 25 ohm.
Okay, so you got incorrect. So this is not the correct answer. So maybe what?
RS
Yeah. So you got 95 ohm, right?
sir 25.
Oh, 25. Okay, 25 is the correct answer. Right. Right. Okay. So you were able to solve all the parts in this, right?
So actually here part I got this little wrong at Z equal to L and T equal to 8 microsecond.
T is equal to 8. Okay. So what we will do, I will go through all the parts. Okay, solution of all the parts, and you can see if it's correct or not, and then you can ask me doubt if you face difficulty in it. Okay. Okay.
Okay, sir.
Okay. Okay, so what I will do, I will go through the solution of this part. Okay, so from here, it's you can see there are two plots, right? So you know at Z is equal to 0, here on the transmission line, the voltage is 100. Okay, so you already know like what is the starting voltage here on the transmission line at Z is equal to 0. Similarly, as you know, like this voltage always takes some finite time to reach to the other end. So now if you go to this plot, go to the other plot, you can see it's taking actually 2 microsecond to for the voltage to appear at the load end, right? So from there you have much many information like what you can calculate. So what you can do here now, these are some of the values which are given. So Z naught is 100 ohm and voltage at Z is equal to 0 between the interval 0 to 4 microsecond is 100 volt. Similarly, the voltage at Z is equal to 0 at t is equal to 4 microsecond is 90 volt. And similarly, the voltage Z is equal to L is at t is equal to 2 microsecond is given by 75 volt. Okay. So in the last tutorial, what we learned, if the battery has some internal resistance, right? So there will be some voltage divide. So voltage will get divide, and then suppose you have any doubt?
No, no, sir.
Okay, okay, okay. I will just mute you. Okay. So you know at the so if you now suppose you are given voltage V naught and you also know internal resistance and you know characteristic impedance. From that you can calculate what will be the voltage here in terms of expression V naught, RS and Z naught, right? So you can write V2 plus. So I'm referring the voltage which is appearing at t is equal to 0 here as V2 plus. Okay. So you can clearly see V2 plus can be written as Z naught upon Rs plus Z naught times V naught. This is because there is some internal resistance of the battery, so voltage will get divided. So this V2 plus will appear at t is equal to 0 on this point, right? So now you know, if I have my battery source as V naught, then V2 plus voltage will appear here. And in the this plot,
Sir, this is V2 plus or V1 plus?
yeah, so basically I will show you, like you can rename it anything. I will show you. Okay. Yeah. So now what you can do, you can actually draw the bounce diagram, right? So here what I have done, I have taken many transit time, right? So at t is equal to 0, I am saying let us take the voltage value is V2 plus, okay? So the same thing will reach at t is equal to 2 microsecond on the other end, right? Because the transit time of this circuit is 2 microsecond, because this is clear from the plots, because voltage is taking 2 microsecond to appear at the other end. So basically from this you can say the transit time is 2 microseconds. So now what I have done here, so I am starting with some V2 plus, and because it's a lossless transmission line, the same voltage V2 plus will appear here, okay, and then it will get reflected from the load end, and then here I am writing voltage V2 minus. Similarly, I am going on the left side now. At t is equal to 4 microsecond, the voltage will again appear on the source end, and here I am saying the value here are V4 plus and V4 minus, which refer to the forward and backward moving voltages. And same you can continue here. So basically the subscript here like V2, V4 just represent the transit time. So here you are right, you can take either V1, V0, whatever you want, but as this is a lossless transmission line, same voltage will appear here, so that's why I took V2 plus here. Okay, so now this is the bounce diagram, okay, for this. Now you need to find volt value of voltages like V2 plus, V2 minus, V4 plus, V4 minus, and similarly V6 plus, V6 minus, and you can go on, right? So V2 plus you already know, right? So what is the starting voltage value? So from here it's already clear that voltage at Z is equal to 0 is 100 volt. So basically V2 plus is 100 volt, right? And now you know the voltage at t is equal to 2 microsecond at the load end is given by 75 volt, right? So if I go here, so basically the voltage here appearing at t is equal to 2 microsecond is 75 volt. That is given from the plots. So now what you can do, you can move forward, and you know at t is equal to 2 microsecond, the voltage at load end is 75 volt. So now at the voltage at the load end is the sum of forward moving voltage as well as the backward moving voltage. So from there you know Vz is equal to L can be written as V2 plus plus V2 minus, right? Because that's what we denoted by the what are the voltages value that is moving forward and backward. And now you know the voltage as Z is equal to L is 75 volt. And you also know V2 plus, which is coming from the source end, is 100 volt, right? So from here you can easily calculate what will be the V2 minus, right? So basically here V2 minus is 25 volt, and here the sign is negative because it's going in the backward direction. Okay, so from this now we know two things. So first we are starting with 100 volts, and we are now moving forward, and as soon as it reach the load end, 25 volt voltage is getting reflected, right? So now you have this much information. From there what you can do, you can go on and try to calculate like what is the reflection coefficient at the load end. So the reflection coefficient at the load end can be written as V2 minus upon V2 plus, right? And it can be also written as ZL minus Z naught upon ZL plus Z naught, right? So now tau reflection coefficient is at L will be minus 25 upon 100, because V2 minus is minus 25, V2 plus is 100, and from there you can write it as ZL minus 100 upon ZL plus 100, and you can solve this thing, right? Because there is only one variable in this equation, which is ZL. So from there the value of ZL you can find is 60 ohm. Okay, so this was the first part of the problem. So it was uh, very clear, like using these plots we are able to calculate the load impedance. So load impedance we got is around 60 ohm. Now our next task is to find what is the reflection coefficient at the source end, right? So that is the second part. Now what you can do, you can again move forward, and you know the at t is equal to 4 microsecond, right? So v at z is equal to 0 is 90 volt. So if you again go here, you know at t is equal to 4 microsecond, the voltage on the source end is 90 volt, right? And if if I go here, so in the bounce diagram, so these are the voltages which we have denoted. So basically at t is equal to 4, you have voltages V4 plus which is incoming and V4 minus which is outgoing. Okay, so from here you can see, as this is a lossless transmission line, right? So V2 minus has to be equal to V4 plus, right? The wave that is coming to the source end, and V4 minus we need to find. So basically you know V4 plus, but V4 minus you don't know, but you know what is the voltage at this end, right? So again it's a easy part and we can move on. So as I told you, the uh, because the V2 minus is equal to V4 minus here, some yeah. So and also if you think, if you need to write the voltage value of V2 minus, right? So that will be tau L times V2 plus. Okay, that is again a okay. That is again a simple thing, because you know the value of voltage V2 minus will be tau L times V2 plus. Okay, and when you again strike at the t is equal to 4 microsecond, the voltage V4 which is going out from the source end, it will be tau L times tau G times V4 plus, right? That's how it works, right? So what we can do here, we can write the voltages V2 minus is tau L times V2 plus, which is due to the reflection from the load end. Similarly, the voltage that is going out from the source end will be a tau S times tau L times V2 plus, right? So these are the voltages which you know now, and you know the net voltage at Z is equal to 0 at t is equal to 4 microsecond is 90 volt. So from here what you can do, you can write the sum as V2 plus. So again, you know how to write the voltage at Z is equal to 4. So basically you draw a line, vertical line at Z is equal to 0 and at t, around t is equal to 4 microsecond, and you start adding the voltages, right? So the voltages that will come in your end will be first V2 plus, and then when you cross here you have V4 plus and V4 minus, right? So the net voltage which is at Z is equal to 0 will be V2 plus plus V2 minus plus V4 plus, which is equal to 90 volt. Okay, that's how what we learn. So whenever you need to find the voltage at some specific end, you just draw a vertical line and see what voltages value are coming in that, and you just sum them all, and that will be your net voltage. Here, because we are trying to find at Z is equal to 0, so if I draw a line at Z is equal to 0, I have this voltage V2 plus, then I have V4 plus, then I have V4 minus. And if someone asks you to calculate at t is equal to 8 also, then you will have like 5 terms. You will have V2 plus plus V4 plus plus V4 minus plus V8 plus plus V8 minus. Okay, that's how it works. So now the problem is only saying us to find at t is equal to 4 microsecond. So this will be the net voltage, which is V2 plus plus V2 minus plus V4 plus is equal to 90 volt. And we know V2 plus is 100 volt, V2 minus is given by tau L times V2 plus. Similarly, V4 plus will be given by tau S times tau L times V2 plus, right? Because there is also a reflection at source end. Now, in this, there is only one variable, right? Because V2 plus, you know, tau L, you know, only thing remain is tau S. So what you can do, you can calculate tau, like from here, you can easily calculate what is the value of tau S from here, right? Because tau L, you know, V2 plus, you know. So if I move forward, I can see 100 times 1 minus 1 by 4, because my tau L will be minus 1 by 4. That is easy to find, because you, if you know the value of ZL, you already have Z naught, you can easily calculate tau L. So the only thing that remains here is tau S, and if you solve this equation which I have marked here, you will able to find tau S is equal to minus zero point 0.6. Okay, so now you have much information. So now you know what is the starting voltage, what is the reflection coefficient at the load end, what is the reflection coefficient at the source end, and now you can move forward and you can solve as many parts as you want. So basically tau load is minus 1 by 4, tau s is minus zero point 0.6, or you can write it as minus 0.25 tau load, and tau s is minus zero point 0.6. Okay, so this was the second part of this problem. So now other part is you need to find the value of voltage V naught. So this is really easy, right? So we wrote this expression, right? So we have V2 plus is equal to Z naught time upon RS plus Z naught times V naught. So V2 plus we already know, which is 100 volts. Z naught we know, right? Z naught is also 100 ohm. RS we know. RS we know, like RS also you can calculate, right? Because if you have value of tau s here, so if you have value of tau s, which is minus 0.6, you can write it as Rs minus 100 upon Rs plus 100, where 100 is the Z naught, and from here you can calculate Rs is equal to 25 ohm. As one of you have answered, they also got Rs is equal to 25 ohm. So the correct answer of first two part is ZL is 60 ohm, Rs is 25 ohm, and similarly we can go on to find the voltage V naught. So V2 plus can be written as Z naught upon Rs plus Z naught times V naught. So V2 plus is 100 and Z naught is 100, RS is 25 and Z naught is 100. So from here you can easily see that the source voltage of the battery is 125 volt. Okay, so now we are able to solve the three parts, and also the transit time, it's clear, it's 2 microsecond. Now we come to the fifth part. Okay, so find voltage on the transmission line at Z is equal to L and T is equal to 8 microsecond. So can anyone tell the answer of this E part, if anyone have solved in the assignment, what value they get? What is the voltage at transmission line at Z is equal to L and T is equal to 8 microsecond? No one? Just tell me the value of.
86.86.25.
Yeah, that's the correct answer. And for the F part, current.
Current Z Z equal to 0, T equal to 8 microsecond. This part.
This current, how much current you got at like find the current at on transmission line at Z is equal to 0.
Z equal to 0, T equal to 8 microsecond.
Yeah, what is the value of current?
1.46.
Yes, so that is the correct answer. Yeah. So, and last part, G also you can tell, then I will go through the solution of all three.
And Z equal to 0.
No. Voltage at, find the voltage on transmission line at Z is equal to L and T is equal to 100 microsecond.
88.24.
Okay, 88.24. Okay, let's see. Let's go through the solution and see. Okay, so our next task is to find the voltage at on transmission line at Z is equal to L and T is equal to 8 microsecond, right? So as you know, like if I ask you like what is the voltage at T is equal to 8 microsecond, right? So as I told you, there will be five sum, right? So when you draw some vertical line and you see at T is equal to 8, there will be five terms. One is V2 plus, other is V4 plus V4 minus, then you have V8 plus V8 minus, and that is the sum of that will be equal to the total voltage at T is equal to 8 microsecond, right? So now let's see. So here uh, at Z is equal to L, you have 4 voltage only. So yeah, so you can write it as V2 plus V2 T is equal to 8. Just a second. Voltage on transformer Z is equal to L. Okay, yeah. So I forgot that in this problem we are asked to at Z is equal to L, right? So we need to draw a boundary at Z is equal to L. So if I draw a line at Z is equal to L and ask for what is the total voltage at T is equal to 8 microsecond. So now you see there are only four things you are crossing. So one is V2 plus V2 minus, then you have V6 plus V6 minus. If the similar thing I ask you like what is the voltage at Z is equal to 0 at T is equal to 8 microsecond, then it will be 5 sum V2 plus V4 plus V4 minus plus V8 plus V8 minus. And the fact that the question is asking the load voltage as Z is equal to L, you will have 4 sum. Okay, so now let's see. So what I have written here, I have V2 plus V2 minus plus V6 plus V6 minus, and that will be the total voltage at T is equal to 8 microsecond at the load end. Okay, so now V2 minus you already know that will be tau L times V2 plus, Similarly, you can write V6 plus, which will be tau L times tau S times V2 plus. Similarly, V6 minus will be tau square L tau S times V2 plus, right? So this is a simple just you are, because every time the voltage is bouncing, it's getting multiplied by the reflection coefficient at load or reflection coefficient at the source. Okay, so this is a net voltage. Now what you can do here, you already know all the values, right? So you know V2 plus, you know tau L, you know tau L, tau S, everything you know. So from there you can go on just calculate the total, what is the value of total sum. So the value of total sum will be 100 times 1 minus 1 by 4, because reflection coefficient is minus 1 by 4. Similarly, because the tau L and tau S both are negative, so it will be 0.6 by 4, because the tau S is 0.6 minus 0.6, so here minus minus is getting plus. Similarly, you have this tau square L times tau S. So basically now here you will have again negative sign, because tau square L will become positive and tau S is negative. So here you will have 0.6 by 16. So now one can actually solve this, and the value of voltage at Z is equal to L at t is equal to 8 microsecond is nothing but 86.25 volt. Okay, so this is the answer of fifth part. Now let's move on to find the current on transmission line at Z is equal to 0 and t is equal to 8 microsecond. So the similar thing works here, but here you just need to find the current, right? So we know one of the easy way to find the current is you just take the voltage and divide it by the characteristic impedance. So what we can do here, we can go on and just draw how the bounce diagram of current will look like. So you have some I2 plus here, same I2 plus is appearing at the load end at t is equal to 2 microsecond, and then you have I2 minus, and similar things goes as we draw it for the voltage. Okay, so now the task is to calculate the every value. So like I2 plus, what is the value of I2 plus, what is the value of I2 minus, what is the value of I4 plus, I4 minus. And similarly, now if I ask you to calculate the current at any time, any Z, you just draw a line and start adding the total currents in that. Okay, so now what we will do first, we will first start by finding voltages or finding the currents of all these values like I2 plus, I4 plus, I4 minus, and similarly I6 plus, I8 plus, and so on. So first of all, as you know, I2 plus is nothing but it is given by V2 plus plus by Z naught, right? So V2 plus is given by how much V2 plus we got? V2 plus is 100 volt, because that is the starting voltage, and Z naught is also 100 ohm. So basically at the t is equal to 0, you are starting with a 1 ampere of current at Z is equal to 0. Now when it hits the load end, you know the I2 minus is given by minus V2 minus by Z naught, right? Because it's getting reflected backward. So basically current is negative. So it is minus V2 minus upon Z naught. So V2 minus, you know, 25, right? Because you have minus minus, V2 minus is also negative, so you will get minus minus, which is equal to 25 volt, and divide by 100. So basically I2 minus is 0.25 ampere. Similarly, if I ask you what is the value of I4 minus, so I4 minus is nothing but V4 minus upon Z naught, which is again equal to 0.15 ampere. And similarly you can calculate what is the value of I4 plus, and because it's from the source end, this will be negative minus V4 plus upon Z naught, and from there you can calculate I4 plus is equal to 0.25 ampere. So you can go on and you can just use simple these formulas, and then you can calculate all the current till you can calculate current at any transit time here. So here we have calculated all the current till 8 is equal to t is equal to 8 microsecond. Okay, so now we have all the values of current, right? So now we can go on and see what the question is asking. So the question is asking, find the current on transmission line at Z is equal to 0 and t is equal to 8 microsecond. Okay, so again, as I told you, to calculate the current at Z is equal to 0 and t is equal to 8, you just draw a line again, and now you see it will be sum of total 5 currents. So it will be sum of I2 plus, it will be sum of I4 plus plus I4 minus, it will be sum of I8 plus plus I8 minus. Okay, so now we can go on and we can write the total current at Z is equal to 0 at t is equal to 8 microsecond. It will be sum of I2 plus plus I4 plus plus I4 minus plus I8 plus plus I8 minus, right? And you have already calculated the values of all the currents, right? So it is I2 plus is 1, I4 plus is 0.25, I4 minus is 0.15, I8 plus is 0.0225, and I8 minus is 0.0375. So if you add all the currents, you will get what is the net current at Z is equal to 0 at t is equal to 8 microsecond. So the answer of this part, which is again F part, is nothing but 1.46 ampere. Okay, and I hope everyone got it correct. If anyone has not got it correct, it's a good time to see where you have made the mistake and correct that. Okay, so now let's come on to the last part of this problem. So now it's asking find the voltage on transmission line at Z is equal to L and T is equal to 100 microsecond. Okay, so basically now you need to calculate like after a very long interval, like at t is equal to 100 microsecond and at z is equal to L. Okay, so on the right boundary at t is equal to 100 microsecond, what will be the voltage? Okay, so one way here I have shown you the very to understand. So first of all, let's see at what interval of time in 100 microsecond voltage will reach the load end, right? So the transit time is 2. So basically first it will strike the voltage at t is equal to 2 microsecond, then it will be t is equal to 6 microsecond, then t is equal to 10 microsecond. So after uh, difference of 4 like 4 microsecond, the voltage will hit the load end. Okay, so now the question is asking to calculate at z is equal t is equal to 100 microsecond. So basically in t is equal to 100 microsecond, it will strike 25 times, because if you add sum of all you will have total of 25 terms. So basically it's striking the load end 25 times in an interval of 100 microsecond. Okay, so now as I told you, if you need to write net voltage, you just need to calculate, like you can go from boundary to boundary. So if I ask like at t is equal to 2, you will say it is a sum of v2 plus and v2 minus. If I ask you at t is equal to 6, it will be sum of v2 plus v2 minus v6 plus v6 minus, right? So similarly you can go on, and now you will realize when you are doing this it will form a very good geometrical progression. So let's see how. So basically if I ask you at t is equal to 2, it will be v2 plus tau l v2 plus, because the reflection coefficient at load is tau l, right? And now if I ask you at t is equal to 6, you will say it is v6 plus v6 minus, and v6 plus is nothing but tau l times tau g times v2 plus. Similarly v6 minus will be tau square l times tau g times v2 plus. And similarly you can go on like this, and you can go up to t is equal to 98 microsecond. Now if you clearly see, because you are adding them to calculate the net voltage at t is equal to 98 microsecond, you can think, let's see if it's forming some geometrical progression. And you already know there will be total of 25 terms like this. So this is one term total, this is second term total, and then you will have till t is equal to 98 microsecond. Okay, so let's see first term. So first term is v2 plus tau l times v2 plus, right? Second term I can write, if I take tau l times tau g common from this t is equal to 6 microsecond expression, you will see it's v2 plus tau l v2 plus. Now you see it will form a geometrical progression where the first term is this, and common ratio is given by tau l times tau g, right? And total number of terms are 25. So now you know the what is the sum of a geometrical progression. So geometrical progression sum is given by a times 1 minus r power n upon 1 minus r, where r is the common ratio, a is the first term, and n are the number of terms. So here a is nothing but v2 plus tau l times v2 plus, right? And r is nothing but tau l times tau g, and n is 25. So basically you can go on and you can calculate the sum. So sum will be v2 plus tau l v2 plus times 1 minus tau g power 25 upon 1 minus tau g, right? So now if you find the product of tau l and tau g, it is very less than 1, because you are multiplying 0.6 up into 0.25. So it will be like this, and when you do the uh, uh, square or any raise, if you raise the power of that, it will be close to 0. So basically this term will be mostly 0 because it's very less than 1. And here you can take the v2 plus out, so it's 100 times 1 minus 1 by 4 times 1 upon 1 minus 3 by 20, right? So from here you can go on and you can calculate the net voltage at t is equal to 100 microsecond by solving this geometrical progression, and you can see the sum is close to 88.24 volt. So this was the answer of the this uh, G part. So this is how you will solve all the problems that are based on these bounce diagram. And if you just know the concept, you know, like hello.
So show that answer again, once again. The
Yeah.
answer it has come 1.46.
Yeah, so I can again go to the one by one to the answer. So the first part was load resistance. So the load resistance is 60 ohm.
Yes.
And then you have
Yes, this is correct.
source impedance is 25 ohm. You have
Yes, sir.
voltage V naught is 125 volt, which is the voltage of the battery. And then you have the voltage at Z is equal to L at T is equal to 8 microsecond
Yes,
is
yes, sir.
86.25 volt. And then you have current at Z is equal to 0 at T is equal to 8 microsecond is 1.46 ampere. And then
So after calculation, I'm getting 1.47. I
mm,
also did this way only, geometric progression, 1 plus.
47, it will be 1.4 because if you keep adding them you will get 1.46 exact. I added them, so maybe you have made some calculation mistake. You can check it once, huh? But your method is correct, right? You so method is same, so answer should be
Yes,
same. Yeah.
yes.
So and the last part was 88.24 volts. Okay, you got this correct?
So for Z equal to 0,
Yeah.
so Z equal to 0, T equal to 8 microsecond,
Yeah.
the current on the line,
F part you are saying, right? F part.
yes, sir.
So
Z equal to 0, T 8 microsecond, current on the line,
1.46 ampere.
yes, sir. This I got 1.46.
Yeah,
But
yeah.
Z equal to 0, T equals to 100 microsecond.
Okay, that part I have not included, but uh, uh, I have not included. I forgot to add last part, but it must be correct only.
Okay, okay.
Yeah. If you have done it this way, it will be correct because once you solve the voltages, it's very easy to get the. Again, you will form a geometrical progression in there, right? Yeah.
Yes, sir.
Yeah,
Yes.
okay. So, okay, so what we will do, this was all about the second assignment. And in the next class, we will be solving the assignment number 3 so that you know all the answers. But before that, what we will do, we will try to solve some of the problem which are related to the week 3. Okay, one, two problems we will solve. So I can just, so what I will do now, I will go to the problem. I have included 2 3 problems for this, which are related to the week 3 assignment. So I will show you the problem and you need to tell me the answers. You can take your time, you can solve them, and then we will go through the solution one by one. Okay. So first problem is this. So let us consider the junction of two lines having characteristic impedance of 50 ohm and other line has a characteristic impedance of 75 ohm. Here you can clearly see it's a two transmission line which have some joint in them, right? And they have different characteristic impedance. Now what you need to do, you need to calculate what is the reflected and transmitted power at this junction. Okay, so please take your time and let me know the answer. So everything is given. You have two transmission line of characteristic impedance 50 and 75 ohm, and you are so I'm asking here what is the reflected and transmitted power at the junction. Okay. So
What is the incident power?
what is the, you can take it P in, you can take it some variable P. Okay.
In
You need to
okay,
tell me in terms of incident power how much fraction is getting reflected and how much fraction is getting transmitted. Okay. So you got the idea, I guess. So please everyone try this problem and let me know the answer. You can take your time. Yeah, it's a very short problem, so just tell the answer. So you need to calculate what is the reflected voltage and what is the reflected power as well as the transmitted power at this junction. So basically some signal is coming, and the fact that there is some reflection coefficient, because they have different impedance, it will get something will get back and something will go forward. So from there you need to calculate what is the transmitted and reflected power at the junction.
So reflective power is 0.04 of incident power.
So reflected power is how much?
0.04
Of,
of incident power.
okay, and transmitted?
Suppose incident power I take Pi, then
Yeah,
0.04 Pi equal
yeah,
to P reflected PR.
yeah. So and transmitted, what is the,
Transmitted 1 minus 0.04 of. Zero point 0.96 of P incident P transmitted.
okay. So looks correct to me. So I urge so that everyone can try, and then we will go through the solution. So if anyone wants to give more answer what they are getting. Right now I have two data points, like reflected power is 1 by 25 of incident power, and transmitted power is 0.96 times the incident power. Yeah. Okay, if no one is answering, what I will do, I will go through the solution. So basically, this is a very simple problem, right? So first of all, whatever is the problem, you first calculate the reflection coefficient. So reflection coefficient will be 75 minus 50 upon 75 plus 50. So the reflection coefficient is 1 by 5, right? And you know the voltages. So basically, if you I am taking, I have some voltage which is going V plus on the forward direction on this first transmission line, and the reflected voltage is V minus, and the transmitted voltage is V1 plus. Okay, this is a simple just model I have taken. And now the fact that tau L is 1 by 5, my V minus will be V plus by 5, right? This is just a simple math where I can calculate V minus, which will be V plus by 5. And now at the junction, you know, there has to be this Kirchhoff's law. So the voltage will be same. So you have V plus plus V minus should be equal to V1 plus, right? So this you know. So the voltage there should be, so you can use this equation, and from there you can see, you know, V plus, you know, V minus, and you can see the value of V1 plus. So the V1 plus is nothing but it is 6 by 5 times the voltage which is coming from the left hand, right? So now you know everything, you know what are the voltages that is getting forwarded or transmitted, right? So the transmitted voltage is 6 by 5 times of V plus, and the reflected voltage is 1 by 5 times of V plus, right? So you know, if you know both of this thing, you know the power is just, you can do directly V into I, and V, you know, V plus by 5, right? Because that is a power voltage value that is getting reflected, V plus by 5. And the current will be, as it's going moving backward, so current will be minus V plus by 5 divided by Z naught, and Z naught is 50. So from here we can calculate the reflected voltage as minus V plus whole square upon 25 times 1 by 50, right? And you know, if the voltage, incident voltage is V plus, what will be the incident power? So incident power is, you can take V square by R. So you can say pi is v plus square upon 50 because impedance is 50 ohm, and then from here you can put the value of v1 square by 50 as pi. So the reflected power is nothing but it's 1 by 25 times of the incident power. Okay, and actually one can actually calculate the transmitted power directly because it has to be conserved. If total is pi and something is getting reflected, so from summation you can easily calculate the transmitted power, but you can also use this way. So the transmitted power is nothing but v1 plus, which is going forward, and the current which is going forward transmitted. So v1 plus is 6v plus 5, and current will be 6v plus 5 upon 75. So don't make this mistake of dividing it by 50 only, because the characteristic impedance of this line is 75 ohm. So when you are writing the current, you need to write it as 75 ohm, right? So just keep that in mind, and then you can just multiply them. This will be 36 times v plus square upon 25 times 1 by 75, and here you can again write, you can multiply 2 on both the side in the numerator and denominator, so that you can get some effective expression, so that you can replace it by pi. Okay, so if I multiply 2 from up and bottom, I will get 36 times 2v plus square upon 25 times 2, which is 50 into 75, and now I can again write v plus square upon 50 as